Hello, hi everyone. So welcome back to the additional session of the synopsis design constraints. So previous time we discussed about design environment where we discussed about set operating condition on the whole design, clock signal going to the clock divider logic, set drive on clock, set driving cell on input signal, set load on inputs, right? Similarly, set wire load for each block including top level, and similarly for output set load, right? And apart from that, set max capacitance, set max transition, set max fan out on input and output ports are current design. So these were some of the things which we discussed in the previous session with respect to the design environment, right? And then we went in detail with respect to set operating conditions, right? So whether it is worst case, best case, how to define them, what are the commands, similarly set wire load model, how to define them, right? And what type of wire load model we are planning to use and from where the wire load model will come, right? It is coming from the Synopsys technology library, right? And then set drive. So set drive is another command where we are trying to specify the drive strength at input port. Okay, then set driving cell. Set driving cell is another command, right? Now similarly set load on the output ports. How to define the set load, right? Then design rule constraints. It can be max transition, max fan out, max capacitance, right? Now let's go a little deeper into design constraints. So what are design constraints, right? So create clock, set clock latency, set clock uncertainty, set clock transition. These are with respect to clock. Similarly, set input delay on input signal, set output delay on outputs, set max area for each block. Similarly, set max capacitance, set max transition, set max fan out on the current design. These are called as design constraints. So please remember, design environment is different, design constraints are different. Now let's go into design constraints as what exactly they are in this session. Okay. Now create clock, right? Create clock command is used to define a clock object with a particular period and waveform. The hyphen period option defines the clock period while the hyphen waveform option controls the duty cycle and the starting edge of the clock. This command is applied to pin or port, right? Now, if you see the command create underscore clock, this command is having period which is defined for the particular clock. Similarly, from where the clock is originating, right? We have to define the ports, right? So get ports is the command, right? So this is the tickle command. Now, let's say there is a clock port. So on this port, we are defining the create clock command, right? And this is the period. So 0 nanosecond to 1 nanosecond to 2 nanosecond, right? So 0 nanosecond to 1 nanosecond. So rises at 0 nanosecond with 50% duty cycle by default. So this is 50% duty cycle. This is another 50% duty cycle. So this is called as TR. Between 0 nanosecond to 1 nanosecond, it is called as TR. Between 1 nanosecond to 2 nanosecond, it is called as TOFF. So T on plus T off is equal to 1 clock period, right? So this clock period is called as 2. Okay. So 0 to 1 and from 1 to 2. So totally from 0 to 2. This is the clock period, right? Now create clock hyphen period 40 hyphen name clock get ports clock. Create clock hyphen period 40 hyphen waveform list 0 20 clock, right? Now this is nothing but your duty cycle. Now as you can see here 0 nanosecond to 1 nanosecond it is having 50% duty cycle, and from 1 nanosecond to 2 nanosecond it is having another 50% duty cycle. So duty cycle of the clock should be 50 and 50. Okay, then only the clock waveform will be proper and it can be recognized by the clock signals, right? So this is create clock. Okay, now modeling clock trees. So design compiler is not used to synthesize clock buffer trees, right? So clock tree synthesis is usually done by a physical or layout tool based on actual cell placement, right? This is logical circuit, this is post layout circuit, right? Now if you see here at the D pin there is data input coming in, right? And at the Q pin of the flip-flop 1, right, the Q pin is giving the Q output which is again going to the D pin, of the flip-flop 2, right? So this is how the edge-to-edge circuitry is. And then the clock signal from the clock port is going to the CK pin of flip-flop 1, and similarly it is going to the CK pin of the flip-flop 2. This is the logical circuitry. Now if you look at the post layout circuitry after clock tree synthesis in physical design, it is something like this. So the clock signal from the clock port is not directly going to the CK pin of the flip-flop 1, it is going through clock buffers. The three buffers which you are seeing here are the inverter pairs which you are seeing here. These are clock buffers and clock inverter pairs, okay, which are specially designed to maintain the duty cycle. So these clock buffers and clock inverter pairs, right, since they are specially designed to maintain the duty cycle, right, they are used in building the clock tree, right? Now from the clock port, the clock signal, unlike in the logical circuit where it is directly going to the CK pin of the flip-flop 1 and flip-flop 2, here the clock signal is going through buffers. That's the difference in the post layout circuit. Okay, it is going to the CK pin of flip-flop 1 and to the CK pin of the flip-flop 2. Okay, that is how it is, right? So modeling clock skew, right? Uncertainty models the maximum delay difference between the clock network branches, known as clock skew, but can also include clock jitter and margin effects. Okay, now uncertainty will include the clock skew as well, right? Since we are now having the clock buffers or clock inverter pairs, the latency difference between the capture flop, which is flip-flop 2, and the latency difference between the launch flop, that is FF1, right? The latency difference between these two is called as clock skew. So this clock skew can be modeled as part of clock uncertainty, set clock uncertainty, right? So uncertainty models the maximum delay difference between the clock network branches known as clock skew, but can also include clock jitter and margin effects, right? So clock jitter is coming from PLL. Now either you can incorporate clock jitter as part of the clock uncertainty, or you can model the jitter separately using the set clock jitter command, or you can model the jitter as part of clock period. So different ways are there to model the clock jitter, right? Similarly, you can even margin the clock latency as well. So that is defined in the uncertainty. As you can see here, TU, right? In the diagram also you can see the TU, which is from the post layout circuit. So TU refers to clock skew plus jitter plus margin, right? This is TU. So as and when you progress in the physical design, you can reduce the TU, right? I mean, once the clock tree is built, you can reduce the clock skew part, right? Later you can even model the jitter as part of the clock period. Similarly, the margin also can be reduced as you move to the sign off tools. Okay, then get clocks, clock CLK placed on clock objects. Okay, now set clock uncertainty and setup timing. Example, create clock hyphen period to get ports clock, set clock uncertainty hyphen setup 0.14 get clocks clock. Right, as you can see here, flip-flop 1 data launch edge, no uncertainty, right? So flip-flop 2 setup check at 2, right? 2 minus 0.14 minus 0.08 equal to 1.78, right? So this is where your uncertainty is coming into picture. So this 0.14 is coming from the setup uncertainty, right? And similarly, the value of 2 is coming from the clock period. Okay, now this is nothing but your max allowable delay for the edge to edge path, and assume lib setup time is 0.08. So this 0.08 is coming from the library setup time, right? So this we normally subtract in the data required time for setup calculation. Okay, so that is where you have only 1.78 as the available time, not the actual clock period, that is 2. Okay, now, modeling latency or insertion delay. Network latency models the average internal delay from the create clock port or pin to the register clock pins, right? Source latency models the delay from the actual clock origin to the create clock port or pin, right? Used for either ideal or propagated clocks post layout. So create clock hyphen period 10 get ports clock, set clock latency hyphen source hyphen max 3 get clocks clock, set clock latency hyphen max 1 get clocks clock pre layout, right? So these are some of the commands which we use to model the latency, right? Source latency, origin of the clock, right? And then network latency. So please remember, source latency is the latency before the clock port, and network latency is the latency after the clock port, right? Now, total latency is nothing but your source latency plus network latency. Okay. Now, pre or post layout clock. So latency, uncertainty, transition, ideal clock. If you see here, in the ideal clock, there is exact duty cycle distribution, that is 50% duty cycle distribution, whereas in the propagated clock, right, there is transition. Because of transition, right, the uncertainty is incorporated here, and then we don't have exact duty cycle distribution. As you can see, the rise transition and fall transition is present here. The more the transition is present, the more the time it will take for charging and discharging, right? And similarly, the internal current consumption will also be going on, which is nothing but part of dynamic current. Okay, because dynamic current is equal to switching current plus internal current. The more the transition, the more the internal current consumption. Okay, now synthesis constraints: reset design, create clock, period is 5. Okay, set clock uncertainty, uncertainty is 0.5, transition is 0.08, clock latency 4, clock latency 2. Okay, this is source, this is network latency, right? Post CTS, if you see here, the period remains same, right? However, the uncertainty has come down. It is now 0.2, okay, from 0.5, right? And there is no clock transition because the tree has been built, okay? And then similarly, set clock latency hyphen source. So latency still remains the same. This is source latency, whereas we don't need the propagated clock latency, right? We don't need the propagated clock latency, and then we need set propagated clock m clock. So this is how the synthesis constraints get mapped into post CTS STA constraints. Okay, now multiple inputs or outputs, same constraints, right? Now if we see, to constrain all inputs the same except for clock port, you need to use this command set input delay. Similarly, to constrain all outputs the same, you need to use the command set output delay. Okay, hyphen max 0.5 hyphen clock. Okay, which means we are giving this 0.5 to the neighboring block in order to perform the into reg operation. Similarly, here we are giving 1.1 as the clock period, right, in order to perform the port to reg operation. Okay, so this is how for all inputs, and this is how for all outputs except the clock port. So we should not define the set input delay for clock port. Okay, now set input delay, these are the commands: set input delay hyphen min 0.0 hyphen clock, set input delay hyphen max 23 hyphen clock, set output delay hyphen max 19 hyphen clock. Set clock latency command is used to define the estimated clock insertion delay during synthesis. This is primarily used during the pre-layout synthesis and timing analysis. The estimated delay number is an approximation of the delay produced by the clock tree network insertion. Set clock latency 3. Get clocks: set clock uncertainty hyphen setup hyphen hold, set clock transition, right, set propagated clock. So these are the main commands which we have to remember either for the synthesis stage or for the post CTS stage. Advanced constraints. So these constraints consist of specifying false paths, multi-cycle paths, max and min delays, group paths, etc. However, use of too many timing exceptions such as false paths and multi-cycle paths causes significant impact on the run times. Right? This is very, very important. So these are all called as timing exceptions. Okay. Set false path hyphen from in one hyphen through u1z to out1. Set multi-cycle path to hyphen from u1z hyphen through u2a to out1. Set max delay 5. Right? This is for all inputs to outputs. Similarly, set min delay all out inputs to all outputs. Right? False path. Timing paths exist in the design, but some of them are not valid functional paths. These paths don't get sensitized under any input vector. SDC commands to set false paths for this circuit are: set false path hyphen from get ports A hyphen through get pins, set false path hyphen from get ports B hyphen through get pins, right? So paths from A to E, right, and B to D, right? So A to E and B to D, right? Please remember here, right? Can never exist. Okay. Now, so A to E, okay, and B to D can never exist. Hence, they should be declared as false paths. Okay. Now, multi-cycle paths. The gate level netlist from synthesis consists of many flip-flops, combo logic flip-flop connections in the netlist as shown below. In STA, the default behavior is to assume the data launched at flip-flop 1 gets captured at the next clock edge at flip-flop 2. Okay, for some paths, it might be intended for the signal to reach flip-flop 2 after more than one clock period. By default, such paths are reported as having violated timing. Paths that need more than one clock period between launch and capture should be declared as multi-cycle paths to ensure false errors are suppressed for such paths. Right? So clock period 2 nanosecond. Data launched by flip-flop 1 takes 3 nanosecond to reach flip-flop 2 leading to setup failure. So SDC commands to define multi-cycle paths are set multi-cycle path hyphen setup 2, set multi-cycle path hyphen hold 1. Right? So these are the commands to define the multi-cycle, which means you are giving 2 clock periods for closing the setup timing, right? Now, generated clocks, right? So create generated clock hyphen name clock A hyphen source clock hyphen divide by 2. These are generated clocks. So we are dividing the master clock with generated clock, right? Now, generated clock. It creates an internally generated clock and defines its characteristics derived from the main clock. It might be divided by 2, 4, or 1. It creates a generated clock in the current design at a declared source by defining its frequency with respect to the frequency at the reference pin. The static timing analysis tool uses this information to compute and propagate its waveform across the clock network to the clock pins of all sequential elements driven by this source. Create generated clock hyphen divide by 2 source get ports clock hyphen name clock A get registers clock divide. Clocking issues. It is necessary to describe clocks in DC such that it imitates the clock delays and skews of the final layout, pre-layout and post-layout. So create clock hyphen period 40 hyphen waveform, right? The same thing will remain in the post layout as well. Set clock latency, we are not getting it into post layout. The reason being, in the post layout, we will have directly the propagated clocks. Then set clock uncertainty hyphen setup. The same thing will be there, except that 0.5 has been reduced to 0.25. There will be no set clock transition, right? And then they will be having set drive 0 clock, set drive 0 clock, because we will not be defining the drive to the clock. Okay. Similarly, operating conditions. So set operating conditions, then wire load models, set wire load model, min block size, set wire load mode, set wire load model, set load wire load selection group. Then system interface. It can be input ports, it can be output ports. Set drive, set driving cell, set fan out, load, set input transition, set load, set port fan out number, right? Design rule constraints. Set max capacitance, set max fan out, set max transition, set min capacitance, right? Timing constraints. Create clock, create generated clock, group path, set clock gating check, set clock groups, set clock latency, set clock sense, set clock transition, set clock uncertainty, set data check, set disable timing, set ideal latency, set ideal network, set ideal transition, input delay, max time borrow, output delay, propagated clock, set resistance, set timing derate. These are very, very important. Then timing exceptions, set false path, set max delay, set min delay, set multi-cycle path. Area constraints, set max area. Multi-voltage and power optimization constraints. Create voltage area, set level shifter strategy, set level shifter threshold, set max dynamic power, set max leakage power. Logic assignment, set case analysis, set logic DC, set logic 1, set logic 0, right? So design, current design, a container for cells, A block, clock, get clocks, all clocks, right? A clock in a design, all clocks in a design, port, get ports, right? All inputs, all outputs, an entry point to or exit point from a design, all entry points to a design, all exit points from a design. Then get cells, right? An instance of a design or a library cell. Get pins, an instance of a design port or a library cell pin. Get nets, a connection between cell pins and design ports. Get libs, a container for library cells. Get lib cells, a primitive logic element. Get lib pins, an entry point to or exit point from a lib cell. All registers, right? A sequential logic cell. So these are very, very important. Then finally write SDC. To write an SDC file directly to a compressed file in prime time, use the -compress ggip option on the write SDC command. Right? Write SDC -compress ggip design.sdc. Then this is another command, read SDC. The read SDC command automatically detects ggip compressed files and uncompresses the files as it reads them. Read SDC design.sdc.gz. Okay. So with this, we'll summarize today's timing constraints topic, and then next week we'll go ahead with some more interesting topics on the timing constraints, and then we'll wrap up the timing constraints topic and move to the next topic. Right? Thank you so much.